Welcome to the Empirical Formulas Labflow experiment number 5. The main objective of today's experiment in Labflow is to understand what is an empirical formula. Also, to observe the laws of conservation of mass and definite proportions. We will go over those shortly. And lastly, you will perform an experiment and calculate the empirical formula of a compound from experimental data. Today's experiment is very simple. We will go over the concepts as I do each week, the concepts in the write-up. You can stop me at any time, and if you are having problems, you can send me a message so I can answer your questions. And after the write-up of the experiment, we will go over some learning checks to make sure you are ready for the pre-lab quiz. And after that, over the report that is really very simple. It's very simple calculation. So after the workshop, I expect you to understand all the concepts and and complete your report and pre-lab quiz with pretty much no problems. So let's look at the beginning. They are talking about background. Okay, they are talking about what is an empirical formula. But before that, I would like you to understand what does it mean in the objectives here that it says observe the laws of conservation of mass and definite proportions. I would like to make sure that you know what it is, the law of conservation of mass. And you are actually, in this experiment, you are going to verify that the law of conservation of mass is true. What is the law of conservation of mass saying? It's saying that the total mass of the substances present at the end of a chemical process is the same as the mass of substances before the reaction took place. What is all this wording? What does that mean? It's actually very, very simple. So just to give you an example, to make it simple to understand what is the conservation of mass. Let's say you have a beaker and you have a liquid and you have a solution, just to say silver nitrate, just to give an example. So you have a solution of silver nitrate aqueous. Very good. And you have also next to it a graduated cylinder filled with potassium chromate, just to give you an example. So we have two liquids, and we are going to take the weight of those liquids. We are going to place them in a balance, and we are going to measure the weight of all these, including the graduated cylinder, or we can include it or not, but we are going to take the mass of the graduated cylinder, of this beaker, and the potassium chromate, and the silver nitrate. We have them separately. And let's say, okay, I look at the analytical balance, I take the weight, and it's showing that the weight is, just to give you an example, 104.5 grams. Very good. Now I want to make sure that the law of conservation of mass is true. So what am I going to do? Well, I will put the potassium chromate into the beaker. I will pour that and I will mix that. And I had two liquids, and now in the beaker, I see that I have a solid. A solid is an indication of a chemical reaction. So the solid is actually silver chromate. So I see an evidence of a chemical reaction. And now I will wait again. After the chemical reaction, I will place it in the analytical balance or any balance, and I will take the weight. For surprise, what happens? The same weight, the same amount of grams. That means it doesn't matter that it was a chemical reaction. The mass before the chemical reaction, the total mass of the elements, in this case, is potassium, chromate, silver, nitrate. Whatever I mixed before, they recombine in a different way, but I don't create matter. So this is essential what it means of the law of conservation of mass. And we are going to use that law in our experiment that is very simple in order to calculate the empirical formula. And the other law here, it says definite proportion. I want to make sure that is clear. What is the law of definite proportion? That is very simple as well, the same as this law of conservation of mass. It's very simple. It says that the name of a compound is always associated with a specific ratio of elements found in the chemical compound. What is this? All this wording means? It means that, let's say I have this compound, H2O. You know that this compound is water. Every time you see a formula with a ratio of 2 hydrogens and 1 oxygen, the name of the compound is going to be the same, and the compound is the same. This is and water is always going to have a ratio 2 to 1. But if I have the same elements and I have a different ratio, I have hydrogen and oxygen, yes, but I have 2 to 2 or 1 to 1 to hydrogen. That means the name changes because the ratio is different and it's a different compound. Is hydrogen peroxide. It's a different compound. It's not water anymore. So then they are talking about what is here in the background. What is an empirical formula? We are going to calculate an empirical formula for a very simple experiment. And what is empirical formula? It's just the lowest whole number ratio of the elements in a compound. I will say it again. Empirical formula is the lowest whole number ratio of the elements in the compound, which means if I have this compound, carbon 6, hydrogen 6, is this an empirical formula? No, this is the molecular formula. Actually, this is the formula of benzene, 6 carbons and 6 hydrogen. But is this an empirical formula? No, because the empirical formula says the lowest whole number ratio, which means that I can actually divide both by 6, and I have carbon 1, hydrogen 1. So the empirical formula is the minimum relationship, is the lowest whole number ratio of the elements in the compound. In this case, carbon and hydrogen. This is the difference. And then they are telling us how are we going to calculate the empirical formula of a compound. In this case, they are giving us an example of calculating the empirical formula of magnesium oxide. But we are going to perform not this one, we are going to perform a different one. Here, we are going to calculate where it says the procedure, we are going to calculate the empirical formula of a compound between magnesium and chloride. Actually, you are going to make a reaction between magnesium and hydrochloric acid. And you are going to form a compound that has magnesium and chloride. So how are you here? If you were in the lab, here is explain what is the setup of the experiment. But even though you are not in the lab, you have to read it because you need to know what you are doing. So when the report comes, you know what to, even though it's very simple in this case, you need to know what to do. So let's review what is the procedure. It's very, very simple. So this is the setup, right? So what you are going to do is you are going, what you see here is called evaporating dish. This is from porcelain. Unfortunately, you cannot have it or touch it, but if you do CHEM 2 in the lab, you will have an opportunity to see it. So you are going to take an evaporating dish, and you are going to place a piece of magnesium. So let me erase this. So you are going to have an evaporating dish, and you are going to have a piece of magnesium metal, and you are going to cover this with this is called watch glass. So the reaction is very, very simple. So first of all, you will place. First of all, you are going to take the weight of just the empty evaporating dish and the empty evaporating dish and the watch glass. You want to know the weight of those because then you are going to add the magnesium and you are going to get the weight of the 3 pieces: magnesium, evaporating dish, and watch glass. So when you subtract the weight of these 3 pieces minus the weight of the empty pieces, you will have the weight of the magnesium metal. You will know how many grams of magnesium are going to react, the mass of magnesium before the reaction starts. And then you are going to add slowly hydrochloric acid in drops until the reaction stops. What is the reaction? So you will have magnesium metal that reacts with hydrochloric acid, and you are going to have a compound that is magnesium combined with chloride and hydrogen. You know the compound, but because we are trying to calculate the empirical formula, all we are trying to do is calculate, let's say, the X of the magnesium. What is this number here? And we are going to calculate the Y. The empirical formula is calculating these numbers, the X and the Y. You know how to write magnesium chloride, but we are going to make sure that this is correct. So we are going to have, let's say, X here, or we are going to have a number here to balance the equation. We know, by the way, that we have seen this reaction in the previous experiment, and we know how to write magnesium chloride. So the purpose of this experiment is to calculate the empirical formula, which means calculating this X and this Y. So how are we going to do? The first step, we already know we are going to place a piece of metal and on the evaporating dish, and by difference we are going to know how many grams of magnesium we have. Then we are going to add drops of hydrochloric acid until the reaction stops. How do we know that the reaction stopped? Well, you see here hydrogen gas, which means that you will see bubbles. That's one evidence of a chemical reaction. So if you see bubbles, means the reaction is still going on. When you see no more bubbles and the magnesium metal is gone, then the reaction stops. And then you will start the flame just to evaporate all the water, because this is aqueous water, and it says here that you evaporate. You start with this Bunsen burner. You start to the heat to make sure that when you are going to wait the second time, you are not waiting water. You have to make sure that you obtain a white powder, a dry white powder. That is your compound. That is your product. So since you are not in the lab, you still have to get familiar with the Bunsen burner and the parts. So watch the videos because they will teach you how this Bunsen burner works. All the Labflow videos, don't miss those because they will teach you the parts of the Bunsen burner and how it works. Okay, so going back, once we obtain the product and it's dry, we are going to weight that again. So that means that we are going to obtain the mass of the product plus the mass of the evaporating dish plus the mass of the watch glass. And then we are going to subtract the mass of the empty watch glass and the empty evaporating dish, and that's how we are going to have the mass of the product. But in order to calculate the empirical formula, we will see in the second part of the workshop, we are going to see some examples, how to calculate it. But we know, because of the law of conservation of mass, that the mass of the magnesium plus the mass of chloride before the reaction has to be equal to the mass of the magnesium and chloride in the product, which means that the mass, let me see if why it's not right. The mass of the magnesium that we already have before the reaction plus the mass of the chloride is going to be the mass of my product, which is this one, magnesium X, chloride Y. And that's how I will calculate the mass of chloride. It's going to be the mass of the product minus the mass of the reactant. But this is the idea how we are going to start calculating the empirical formula. Any questions before we go to the practice problems? You can message me. Awesome. Okay. Let's look at the practice problem before we go into the report. So you can actually text me or send me a message. Which formulas below are empirical formulas? A, you can say yes or no. I will look at what you think. No, very good. Exactly. The empirical formula is, well, let's pay attention. If we say CA, close. How do we get the empirical formula? We look at these two and we look at these six. We need whole numbers, and the smallest number is the 2. So if I divide both subscripts by the smallest, yes, awesome, Karen, awesome. The empirical formula is CH3. Awesome, very good. Now B. Is B an empirical formula? Yes. How about C? No, very good. Exactly. Awesome, Karen. How about D? Yes, awesome. That is the empirical formula. How about E? Is an empirical formula? Yes, awesome. How about F? Exactly, very good. This is the empirical formula. And how about G? We have to find a number that we can divide both. Is not an empirical formula. Very good. And now which one is? We have to find a number. Exactly. Very good. Awesome, Karen. Great. Okay, so we know what is an empirical formula. Let's look at the example number 2. Take your time to read it. It says 0.245 grams of powdered copper metal is roasted in oxygen, which means copper is reacting with oxygen. The product is weighed and found to be 0.304 grams. This is after the reaction. What is the empirical formula for this compound? So we have the initial weight of the copper, and the final weight. So the first thing that we know, what do we know? That we have a reaction between copper plus oxygen, and we have a compound between copper and oxygen. And our job is to calculate this X and Y. The first thing that we are going to do is to determine the number of grams of each element. In this case, the reactants are copper and oxygen. We need to know how many grams of each. So we know that we have 0.245 grams of copper. And we also know that we have 0.304 grams of product. And we know that the mass of copper, because of the law of conservation of mass, equals the mass of copper in the reactant side is the same as the mass of copper in the product side. And we know that the compound is only formed by copper and oxygen. So what is the mass of oxygen? The mass of oxygen is going to be the difference, 0.304 grams minus 0.245 grams. If you do that, you are going to obtain a mass that is 0.059 grams of oxygen. So we did the first step. What did we do? We have the grams of copper and the grams of oxygen. What is the second step in order to calculate the empirical formula? We have to convert grams into moles, because we are looking, remember the empirical formula definition is the lowest whole number ratio of elements. So we need to convert grams into moles, and that is actually very easy. We only need to look in the periodic table. We need to look at the molar mass or the atomic weight of the oxygen, which is 16, and the same with copper. So let's look at when we are going to convert number of moles, the number of moles of oxygen is going to be the grams of oxygen, 0.059 grams, multiplied by, we know the atomic weight. We know that 1 mole of oxygen has a weight of 16 grams. It's hard to write with the mouse. So you are going to obtain a number of moles that is 0.00369 moles of oxygen. And then we have to do the same for the copper. So what do you obtain for the copper? You can do it on your end and tell me. I'm trying to calculate the number of moles. I did the oxygen, but I have to do now for the copper. So how many numbers of moles is going to be for copper? 0.245 grams. The atomic weight of the copper is 63.55. How many moles of copper do you obtain? What is your answer? Do you have a calculator? You can text me, send me a message. This is the number I obtained. Okay, so what did you do? Let's see. What we are trying to do is just convert the grams into moles. That's all we are going to do. We are dividing the grams by the atomic. That number, it doesn't make much sense. So what okay, I'm not sure what you did, but let's take a periodic table. Let me see if I have one close by. When you look in the periodic table, look at the copper. What is the atomic weight of the copper? I see 63.546. Yes, awesome. Okay, so all you have to do is divide 0.245 grams by that number. What did you obtain? Let's try again. (0.245 divided by 63.55. I keep saying, okay, let me try with mine. I get 0.245 divided by 63.55. Yeah, okay, I get 0.00386 moles of copper. I can stay. Okay, so then I will stay at the end and see what's happening with your calculator. Somehow I'm not sure. After I finish the recording, we'll go over that. But in this case, the second step is how do you convert grams into moles of the same element? You just divide by the atomic weight. So in our case, let's see, we have this number of moles of copper, and we have this number of moles. We are very close to the empirical formula. Very, very close. What is the next step? See that both numbers, these two, are very close to each other. And we have to pick which one is smaller, which number is smaller. And we divide by the smallest number, because what this means, actually, when we calculate the number of moles, exactly, very good. So now we divide both by that. So we are going to divide. What does it mean, what we calculated so far? We are trying to calculate X and Y, right? Copper, oxygen, Y. So far, we calculated that the copper has 0. This is the ratio, 0.00386 386 moles, and the oxygen has 0.00369. So far, we know this, but because we need whole numbers, that's the last step. The last step is dividing both numbers by the smallest number. In this case, 0.00386, which means it's going to be a 1. And this one that is very close, 0.00386. I divide by the smallest number, and then I round it, and my empirical formula is 1, 1. So this is the answer. Any questions on this? Okay. So just to review, the empirical formula, the first step is always calculating the number of grams of all the elements involving in the reaction. Then we convert it into moles, and then we divide by the smallest number. So this is what we are going to do in our experiment today. So let's look at our last example before we jump into the report. It says, what is the chemical equation? Let me see. What is the chemical equation? Let me try to make it bigger. Okay. What is the chemical equation for the reaction between magnesium and hydrochloric acid, which is what we are doing? How do you know the reaction is performed to completion? Okay, so by now, even though we are going to demonstrate how to calculate the empirical formula, you have this reaction from the previous experiment. So this is the chemical reaction. Magnesium chloride plus hydrogen. And how do we know that the reaction is performed to completion? We know that there is no more magnesium. The magnesium is gone, disappeared, because it converted into this white powder. That is one sign. And another sign is that the hydrogen is a gas. When we see no more bubbles, that's another indication that the reaction went to completion. Any questions? Okay, so now we are jumping into the report that is actually very simple. When you are going to open your report, you are going to see that because you didn't do the experiment in the lab, you will be given the mass of the watch glass. Every person has different data, so it doesn't matter. So you are going to be given the mass of the watch glass, an evaporating dish, empty. Before the reaction, the mass of the watch glass, the evaporating dish, and the magnesium. And then you are going to be given, after the reaction, the mass of the watch glass, evaporating dish, and the magnesium after it reacted and after cooling, because you can never wait when something is hot. You have to wait until it's room temperature. So the first question that they will ask you here is calculate the mass of magnesium. You send me a message and tell you how are you going to calculate the mass of magnesium using this data that is given here. You can use my data because you are going to have a different data. Subtract. Excellent. What are you subtracting? You want the mass of magnesium before it reacted. So what? Yes, awesome. Exactly. Exactly. You are going to do that. 51.61 minus 50, the empty. Exactly. Exactly. Very good. How about the second one? The mass of the product. You got, let me get the other number. Yes, okay, you are close. You are good. The first number is correct. You said 52 point, that is, where did you get that number, the 52.8? So the mass of the product, after everything reacted, you want just the mass of the product, but you don't want the mass of the watch glass and you don't want the mass of the evaporating dish, but you want the rest. So all you have to subtract from 52.32 is what? The two things that you don't want, which is the empty evaporating dish and the empty watch glass. Does it make sense? Okay, great. So now we have the grams of the magnesium, we have the mass of the product, but we saw in our example, how are we going to calculate the mass of chlorine? We saw that we have to subtract the mass of magnesium because of the law of conservation of mass. We know that this actually is the mass for us, the product, and this is the mass of magnesium. If you subtract both, if you subtract the mass of the product minus the mass of magnesium, you are going to obtain, in this case, with my data, grams of chlorine. Does it make sense? Awesome. Okay, now that we need the data of, we need the mass of magnesium and we have the mass of chlorine. All I have to do is convert it into moles. They ask you for the moles of magnesium, moles of chlorine, and then calculate the empirical formula in the same way that we did it. So how are you going to calculate the number of moles in the product? You know that you have 0.24 grams. Let's 0. Perfect. Let me see. Which number did you get? Let me check in the. Okay, how did you get that? With our, how did you get that one? You have 0.24 grams, right? I think it's your calculator that is tricking us. 0.24 grams of magnesium. Yes, I know, I'm not sure what is happening. So you have 0.2 grams and you divide it by what? By the atomic weight of magnesium, right? Yes, exactly. 24.31. When I do that, I get a number like 0.00987. That's my number, basically 0.0099 moles of magnesium. And then you do the same with chlorine, but you divide by the atomic weight of the chlorine, that is 35.45. And once you have that moles of chlorine, you are going to calculate here the empirical formula. You are going to see this divide by the smallest number and get the empirical formula. Any questions? So I will stop the recording now. I want to thank you for being here, and I will stay to answer additional questions. Thank you again.